Adventures in Electricity. Chapter 1. The Spark of Discovery, 1700s. Electricity has always been around. It flashes in the sky as lightning and crackles when you shuffle your feet on a carpet and touch a doorknob. But in the 1700s, nobody really understood what it was. That's when Benjamin Franklin, inventor, printer, and scientist, stepped onto the stage. In 1752, he launched one of history's boldest science experiments, flying a kite in a thunderstorm. He tied a metal key to the kite string, and when lightning struck, sparks danced from the key. Dangerous? Absolutely. But Franklin had just shown the world that lightning and electricity were the same thing. Battery power, then and now. Franklin also gave us words we still use today. One of them is battery. Back then, he used the term to describe a group of Leyden jars, glass bottles that stored static electricity. Today, the word battery means a container of stored energy, whether it's in your phone, a flashlight, or a car. The magic of the Leyden jars terminal. Electricity was a mystery. Before Franklin, natural phenomena like lightning and static shocks were observed, but the underlying science of electricity was not understood. Franklin's risky proof. In 1752, Benjamin Franklin famously proved that lightning was a form of electricity using a kite and key experiment, which was both groundbreaking and dangerous. The power of terminology. Franklin introduced essential electrical terms, including the word battery, which originally described his method of grouping storage devices, Leyden jars, and is now used for modern power storage devices. Chapter 2. Spinning Power, 1800s. In the early 1800s, electricity was still more curiosity than tool. But step by step, scientists discovered how to make it practical. Electromagnetism. In 1820, Hans Christian Ørsted found that an electric current in a wire could make a nearby compass needle move. This showed that electricity and magnetism are connected. André-Marie Ampère quickly expanded on this, laying the foundation for the science of electromagnetism. Electromagnetic induction. In 1831, Michael Faraday made the next giant leap. He discovered electromagnetic induction. When a magnet is moved near a coil of wire, it makes electricity flow. This was huge. Instead of just using stored charges, like Leyden jars, scientists could now generate electricity on demand. Faraday built the first electric dynamo, a simple generator. Though small and inefficient, it showed how moving magnets and coils could create usable current. Almost every modern power plant, from coal to nuclear to wind turbines, is based on this same principle. Faraday's work led to different ways of sending electricity through wires. By the late 1800s, inventors like Thomas Edison pushed direct current, DC, electricity that flows in one steady direction. Others, like Nikola Tesla, championed alternating current, AC, electricity that rapidly switches direction many times per second. The stage was set for a major debate over which system would power the world. Electricity became more than sparks and jars in the 1800s. Scientists across Europe started to uncover the deep connection between electricity and magnetism. These discoveries transformed electricity from a curiosity into a usable force.
Hans Christian Ørsted, 1777 til 1851.
Ørsted was a Danish physicist who, in 1820, made a simple but powerful discovery. A wire carrying an electric current could move the needle of a compass. This was the first evidence that electricity and magnetism are linked. Key idea: electric current produces a magnetic field. Legacy: opened the door to the field of electromagnetism.
André-Marie Ampère, 1775-1836.
Inspired by Ørsted, Ampère expanded the study of electromagnetism. He showed that two wires carrying current could attract or repel each other, just like magnets. His work explained how electric currents can create magnetic forces. Key idea: currents interact like magnets. Legacy: the unit of electric current, the ampere, amp, is named after him. Michael Faraday, 1791 to 1867. Faraday took the biggest leap forward in 1831. He discovered electromagnetic induction. Moving a magnet through a coil of wire makes electricity flow. This is the principle behind all modern generators. Key idea: moving magnets near coils generates electricity. Legacy: the father of electricity. Without Faraday, no power plants, no electric motors, no modern world. Electricity on the move. By the late 1800s, Faraday's discoveries made practical electricity possible. Engineers could generate current using machines instead of storing small sparks in jars. But there was still debate over how electricity should be delivered. Direct current, DC steady flow in one direction, pushed by Edison. Alternating current, AC back and forth flow, switching direction many times per second, championed by Tesla. Key ideas: electricity and magnetism are two sides of the same force. Moving a magnet near a wire makes electricity flow, electromagnetic induction. Current can be direct, DC, or alternating, AC. Chapter 3: The Age of Power and Light, late 1800s. By the late 1800s, electricity had moved from being a curious experiment to something that could change entire cities. Thomas Edison gave us the light bulb and believed in direct current, DC, electricity flowing in one direction only. Nikola Tesla promoted alternating current, AC, which could travel long distances because it switched directions back and forth many times per second. Edison versus Tesla. The rivalry between Edison and Tesla, called the War of Currents, shaped how electricity reached homes, factories, and schools. With help from George Westinghouse, AC systems spread across cities, and electricity began powering machines, streetlights, and whole neighborhoods. That's why people started calling electricity power, because it replaced the muscle of people and animals with something stronger, cleaner, and brighter. Chapter 4: Chasing the Sun and Beyond, 1900s, 2000s. Building on Faraday's induction, the 20th century brought new ways to generate electricity without burning fuels. Scientists learned that certain materials release electrons when hit by sunlight. This is called the photovoltaic effect, first explained by Albert Einstein in 1905. By wiring many of these solar cells together, we can turn sunlight directly into electricity. Key idea: sunlight solar cells electricity. Term: photovoltaics, converting light into electric current. This era also saw other clean energy sources. Wind turbines and hydroelectric dams use spinning blades, like Faraday's dynamo, to generate power from wind or water. Nuclear power, developed in the 1950s, splits atoms to create heat, which turns water into steam to spin turbines. These advancements made electricity more sustainable, reducing pollution and reliance on coal. Chapter 5: Measuring Electricity, Volts, Amps, and Watts. Electricity is invisible, so how do we measure it? Scientists created special units to describe how it moves and how much work it can do. Think of it like describing a river. You need to know how fast the water flows, how much water is flowing, and how much total energy the river can deliver. Volts, the push. Definition: voltage is the push that makes electrons move. Analogy: imagine water in a hose. Voltage is the water pressure, how hard the water is being pushed forward. Story: Benjamin Franklin didn't use the word voltage, but his experiments with stored sparks in Leyden jars showed the idea. The stronger the push, the bigger the spark. Alessandro Volta invented the first battery, voltaic pile, in 1800 using stacked zinc and copper discs separated by salty paper, creating a steady voltage. Unit: named after Alessandro Volta. Amperes, amps the flow. Definition: amperage measures how much electricity is flowing. Analogy: in our hose, amperes are like the amount of water coming out per second. A trickle is low amps. A fire hose blast is high amps. Story: André Marie Ampère studied how currents behave and gave us the foundation of electromagnetism. His name lives on in the amp. Unit: 1 amp equals 1 coulomb of charge flowing per second. Watts, the work done. Definition: wattage measures the power, how much work electricity does per second. Analogy: if voltage is the pressure and amps are the flow, then watts are the total water splashing out and turning a water wheel. Watts equals volts times amps. Story: James Wood improved the steam engine, and his name became linked with power, the rate of doing work. Unit: 1 watt equals 1 volt times 1 amp. Major volt, Dr. Watts, superamp. Pulling it together. Electricity can be summed up like this. Volts equals push, like water pressure. Amps equals flow, like how much water is moving. Watts equals power, like how much work the water does. That's why your light bulb says 60 watts, your phone charger says 5 volts, and your fuse box lists 15 amps. Each tells you something about the energy running through your wires. Chapter 6. Inside the Atom, the Secret of Electrons. Electricity doesn't start with wires or light bulbs. It starts with the tiniest building blocks of matter, atoms. The discovery of atoms. Long ago, Greek philosophers like Democritus, around 400 BCE, imagined that all matter was made of tiny, invisible pieces he called atomos, meaning uncuttable. But for centuries, this was just an idea with no proof. In the 1800s, scientists like John Dalton proposed that atoms were real. Later, experiments by J.J. Thomson in 1897 revealed something even smaller, the electron. He showed that these particles carried a negative charge, and they were part of every atom. This was the first step in linking atoms to electricity. In 1911, Ernest Rutherford discovered the nucleus, showing atoms have a dense center. The atom up close. Every atom has 3 main parts. Nucleus, the center, packed with protons, plus, and neutrons, neutral. Protons give the atom its positive charge and determine its element, e.g., hydrogen has 1 proton. Electrons, tiny, fast-moving particles that orbit around the nucleus in shells. They balance the proton's charge. Magnetic field. When electrons move, they create invisible magnetic fields, tying back to Ørsted and Ampere. The key to electricity is this: electrons can move. In some materials, like copper, the outer electrons are loose and can jump from atom to atom. That's what makes copper such a good conductor. When electrons all move together, that flow is what we call electric current. Story connection. Think of electrons as tiny messengers. In metals, they're not stuck at home. They're free to travel down the street from one house, atom, to the next. When a battery or generator gives them a push, the whole crowd of electrons moves in one direction. That movement is electricity, and it lights our lamps, charges our phones, and runs our machines. Conductors, insulators, and more. Conductors, like metals, allow easy electron flow because outer electrons are free. Insulators, like rubber or plastic, trap electrons tightly, preventing flow, great for safety, like coating wires. Semiconductors, like silicon in between, they conduct under certain conditions. Invented in the mid-1900s, they're key to computers and solar cells. Chapter 7. Electricity's Bright Future. From Franklin's kite to solar panels on rooftops, electricity has powered our world for centuries. Today, it's evolving with electric cars, like Tesla's, named after the inventor, smart grids, and AI that optimizes energy use. By chasing clean sources like sun and wind, we can make electricity sustainable for everyone. Remember, you can see the world from space because of those tiny electrons. Everything is brighter with electricity. Thanks, amigos.